In the beginning, it is hardly apparent amid the numerous light sources filling the sky. This space region is far from black because a million stars shine there, clustering there 100 million times more strongly than they surround the Earth. A group of suns in the center spin quickly, spiraling towards the center of the star's orbits, a single unchanging point of light. The peculiarity of this center body starts to become apparent at this point. The target appears as a sizable luminous ring that is cross-cut right beneath its equator and is filled at its core with a darkness that is even darker than the encircling void, rather than a smooth circle of light as it would appear in the crosshairs. This is where the black hole comes into view. Until now, you had moved independently in the direction of this intriguing body, but there is now a slight tugging in that direction. You are placed in a ring around its center alongside a luminous band of material that is accreting and is being cinematized into a rim by strong gravity. You are battered and slammed by rapidly moving gas, dust, and debris inside the accretion disk. Additionally, the entire disk radiates at high energy due to tremendous frictional heating bombarding your body with X-rays and gamma rays. Your DNA is irreparably ruined, but it won't matter very soon, because at this moment, reality begins to falter. While black holes have the potential to cause destruction, their supermassive counterparts can feed and sustain the fundamental elements that give rise to stars, planets, and life. But a lot of these gigantic black holes also raise questions for us. How did they initially become so prominent? What were their roots if they were the galaxy's seedlings? And what were the first black holes? And when were they created? Join us till the end of this video as we dive deeper into the history of the black hole. The first black hole. In 1915, during World War I, Lieutenant Carl Schwarzschild received a letter from a close colleague named Albert Einstein, which contained the conceptual foundation for the general theory of relativity and all of our current knowledge of gravitational effects on cosmic scales. It outlines in exquisite mathematics how matter induces space to curve and how space-time instructs matter on travel, making it incomprehensible to all but the most sophisticated theorists. A few days later, Schwarzschild writes back to his friend with the most out-of-the-box solution. He started his letter by saying, "As you see, the war treated me kindly enough, despite the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Schwarzschild discovered a straightforward explanation for how space-time curves around spherical objects like planets and stars during his relativistic walk. By extension, he demonstrated how it becomes much more difficult to flee the gravity of a modest, compressed, and highly complex star. He also demonstrated how, by exceeding the star's maximum density and further condensing it, the curvature becomes so extreme that no particle, not even light photons, can escape. The Schwarzschild radius, so named because it relies on the universal gravitational constant, the speed of light, and the amount of mass concentrated in one location, is the distance from a given point at which nothing could escape. The Schwarzschild radius only hinges on mass because gravitation and the light speed are constants. The more mass, the wider the radius reaches. For instance, a human's Schwarzschild radius is approximately a millionth the size of a single quark. Thus, if you were compressed down to this size, you would be trapped there forever by the force of gravity. It is around 9 millimeters around the Earth and 3 kilometers around the Sun. Naturally, since these bodies' actual diameters greatly surpass their Schwarzschild radii, their mass isn't concentrated within them. Thus, we don't observe any peculiar behavior. Schwarzschild concluded that this severe space-time curvature would only be noticeable in the circumstances of very dense objects. Schwarzschild managed to escape the gunshots, but he shortly passed away from a skin condition he had picked up while fighting. He didn't live long enough to witness how his concepts would be expanded. Many physicists at the time refuted the possibility of such an incredibly dense object and the corresponding space-time curvature. To look for astronomical sources of X-rays, which are often blocked by our dense atmosphere, 2 Geiger counters were deployed in 1964 in a brief rocket journey above the atmosphere. One such potent X-ray source, which came to be known as CUIGX-1, was found by these instruments as they swept across the sky. Its exact essence was a mystery for some years because the bright X-rays didn't appear to connect with any notable star or body that could be observed. Later, more accurate observations were added to the evidence supporting astronomers' growing suspicions. Because of the source's extremely rapid X-ray variability, which occurred on timescales of less than a millisecond, It was inferred that the X-ray generating region was much smaller than that of a typical star. Furthermore, identifying a binary companion made it possible to determine the source's mass by assessing the size of the partner's orbit. The outcome was astounding. CYGX was around 15 times greater in mass than a star while being smaller. The most plausible explanation is Schwarzschild's light-swallowing singularity because it is significantly beyond the theoretical maximum for white dwarfs or neutron stars. Its secrets were being solved through the early 1970s, and science had also given this gravitational monster a new name. After World War II, American theoretical physicist John Wheeler took it upon himself to rekindle his interest in the general theory of relativity. In a 1967 lecture at NASA, a lecturer who was sick of hearing him repeat the phrase gravitationally completely collapsed object, for the zillionth time suggested the term black hole as a substitute. Wheeler grabbed onto the brief yet potent phrase. Black holes gained widespread recognition from then on and became a household name. Today, scientists have a solid grasp of how some black holes, such as CYG, form. Stars burn fuel made of hydrogen and helium until that fuel runs out, at which time the heat produced by fusion is insufficient to keep them from collapsing under the force of gravity. Supermassive. 10th of April 2019. A photo suddenly becomes a media hit and travels the world. Contrary to most viral photos, this one wasn't particularly eye-catching, even if it was hazy and illegible, an orange torus on a simple black background. It nonetheless represented the labor of dozens of researchers throughout a half-decade. Only a few weeks later, billions of people had seen the object that physicists had long denied, in which the majority of astronomers never anticipated witnessing in person. Of course, it was the first ever picture of a black hole. As implied by their name and description, black holes are always dark in color. This gives the idea of taking photos of them a first impression appearance of being a fool's errand. But the voraciousness of these gravitational gulfs and their repercussions on the stuff around them have caught the attention of scientists. Theoretically, a sufficiently enormous black hole encircled by a vast disk of gas and debris emits enough high-frequency radio waves to be picked up by a sufficiently massive radio telescope on Earth. The black holes are required to be supermassive, which is the term for a black hole that weighs millions or even billions of times that of our Sun, to be light enough to be seen. According to astronomers, these titans are found at the center of most massive galaxies and may have played a significant role in the creation and development of the galaxies themselves. Contrary to logic, the supermassive occasionally spew out accelerating globules of gas as they consume and expand, which helps stars form right before others die. Since there is such a close connection, some astronomers debate which came first. Did the first galaxies support and feed supermassive black holes? Or were they already there? After another couple of years of committed research, scientists discovered another black center in the universe known as M87, thus the Large Millimeter Telescope. The Very Large Array and the giant Ukrainian radio telescope came into being. However, even the Very Large was insufficient for M87. It would be necessary for the radio telescope to be about the diameter of the entire planet. 8 radio telescopes were linked together by researchers from around the world, creating a combined telescope with an aperture that extended from the South Pole to Spain with a resolution about 4,000 times better than that of the Hubble Space Telescope. For 4 days in 2017, this Event Horizon Telescope, which had its parts synchronized by an atomic clock, gathered radio waves from the direction of M87. Due to the volume of data each monitoring station produces, the observations were supplied on physical hard drives instead of the internet. The researchers finally obtained their impossibly difficult image after 2 years of extensive data processing. An outline of the M87 supermassive's black hole event horizon illuminated by the radio waves of its accretion-discretion disk. But the discoveries kept coming. Data from the Event Horizon Telescope's initial observations of the Milky Way were completely addressed in the second image of a black hole in May 2022. Following an extra 3 years of processing, we finally caught sight of the pulsating core of our galaxy. Sagittarius supermassive black holes are becoming more and more understandable through imaging and analysis. However, there are still many doubts about their existence and, most importantly, how they formed. That was all for today. If you liked this video, hit the like and subscribe and let us know in the comments below what more you would like to see from us. Till then, stay tuned and connected.